This is the desktop dynamometer. What you're looking at here is a 4-stroke gasoline engine. It's got its controls for throttle and the kill switch. It's connected to an aluminum plate. This is the eddy current aluminum plate. That's all it's connected to. What you see on this side is this is the actual dynamometer. The dynamometer consists of a couple electromagnetic coils which are suspended in a bearing rest. This allows it to freely rotate. Now it has a spring which is pulling it down and putting it in contact with a load cell. This load cell is then measuring the force or the torque on these coils. When we put current through the coils, it induces eddy current in this aluminum plate. If the plate is spinning, it resists the motion of the plate, loading the engine, and we can read the load in this load cell here. The information coming from the dynamometer and the control of the dynamometer takes place in this. This is the dynamometer controller. Dynamometer controller, it has several different modes, a manual mode, a speed control mode, torque control mode. On the display you can see the speed here, the torque, and your percentage load. Also, the data is being sent to a computer for data logging, saving, and analysis. It displays a log of the data here. It also displays a power and torque curve here as a function of speed. Later you can go back and analyze the data.
We're in manual mode with no load, so we've got a high speed and no torque. As I increase the load, the speed will start to come down and the torque will start to go up. You can see the same thing. So the speed comes down and the torque goes up. You can see the same thing on the computer. As we increase the load, the speed comes down and the torque goes up. If I decrease the load, we'll follow the torque curve back up again. And now my speed is going up. My torque will go down. We're producing no torque at this point. It's the no load torque point. We can follow the torque curve by slowly increasing the load. So our load here is 37% and going up. We go to our maximum power point, and then power drops off. Our torque is still climbing, but as we go down, our torque curve starts to drop off too, until we stall the engine completely. Now we've stalled the engine. There's our power curve, there's our torque curve. Here we have an electric motor, a very small electric motor, coupled to an eddy current disc to the desktop dyno. Desktop dyno is exactly the same, very easy alignment procedure. You simply mount it on there. This is a very small motor. Its capacity is only 80 watts compared to the 2 kilowatts we get out of a gasoline. Very small electric motor, spinning at about 6,000 RPM with no load. We can come over here and apply load to it once again. Slowly apply the load, and as we apply load, we'll see that the motor starts to slow down. As it slows down, the torque will go up. Because it's an electric motor, the torque goes up very slowly. Essentially, the torque curve is rather inversely related with the RPM. This is data captured using a different screen capture. Again, we're looking at the torque and the power of the electric motor as we apply more load using the dyno. You see that there's a linear increase in torque as speed decreases and a parabolic power curve. You look at theory for the same motor and you see the same thing. A linear increase in torque as the speed decreases and a parabolic power curve. So in this case, our experimental data matches very well with theory.